Once again, let's use Python to take a look at what we've seen. So we can try out this factorization, for instance, if we use the SymPy, the symbolic mathematical package, and observe that the exponentiation in Python is symbolized with 2 stars. So here from SymPy we're importing all, and from SciPy we are also importing everything. Here we are defining z as a symbol. We define n equals to 4, and we are having a baseband prototype which is from H0 to H7 as symbols. So the MDCT polyphase matrix H, we are doing this here. Since each column contains the time reversed impulse response, we need n minus 1 minus n instead of n. And we start with a n by n matrix of zeros. So what we're doing, we're having a matrix of zeros, n by n, and then we are going n going from 0 to n, and k also going from 0 to n, and here we have our n minus 1 minus n, and this will give all the elements for our matrix, and this is the equation we've seen before. Here we have our z to the power of minus 1, and here we would have our z to the power of 0. So then the transform matrix T for the DCT4 is given here. And now our sparse matrix FA is the H, which we computed here, times T here to the power of minus 1. And then we will print this matrix. And this is what we have. This is our matrix H. And this is our sparse matrix FA. Here we see that it's the same as equation 3, apart from some rounding errors, and that we get a diamond matrix shape. This diamond shape results from the time shift of n divided by 2 in the cosine modulation function. It has the effect of shifting the left and the right halves of the above cross-shaped matrix and multiplying it with z to the power of minus 1. The result of shifting or exchanging those two halves in this diamond-shaped matrix that we can see here. This matrix is now surprisingly simple. It only contains the 2 times capital N samples of our baseband prototype impulse responses. Most entries are 0, and we have delays of z to the power of minus 1 only on the left side. We have z to the power of minus 1 here on the left side. And this was the purpose of the sum capital N divided by 2 on the cosine modulation function. In this way, we can factor out the delays using what we will call a delay matrix, which is very important for invertibility and perfect reconstruction. The particular diamond shape of the matrix results from the symmetries of the cosine modulation and the shift of capital N divided by 2 on the modulation function for the time index.